It's my pleasure to be here. I want to thank Dr. Tedeschi to invite me here. And as you just heard, my background is computational astrophysics. I was doing simulation for black holes and neutron stars about 10 years ago. And then I joined ASAS-NANP as a research scientist working on big machines, supercomputers, and then started working on different data analytics and numeric modeling projects, and then became a tenure-track professor. That's like a long track of academia. Oh, I'm not sure if, do I need to click the recording here? Okay, it's already recorded. Good. So again, so we have this project started a couple of years ago. It's already, I believe, more than a year. It's a collaboration between IM Engineering, Animal Science, and Life, and also our brand new school of Performance Visualization and Fine Arts. So this is me, and I'll put it in the slide just in case you want to reach out to me, and I have contact information here. And the slides will be shared. I think the one you got previously might have the volume message at the bottom, but I'll share the whole slides with you all afterwards. So again, we, as just mentioned by the host here, we started the Digital Twin Lab last October. The goal of Digital Twin Lab is to build technologies and develop technologies and new algorithms that can make life easier for people to build digital twins. That's why I'm here. Actually, I'm just trying to show you some simple example and some big frameworks and you can think about. And probably you don't have to do everything exactly the way I do it, but the way we do it might be provide some, guidance and probably give you some, feedback about give you some hints about what you want to do if you want to build a digital twin. So for today, we'll start with 20 minutes introduction. And we have some applications and some background knowledge about digital twins, because digital twin itself is a very interdisciplinary field. It's not brand new, but it's relatively new compared to many other fields. And I'll introduce a little bit about deep learning. If you are new to deep learning, you can get some, learn something probably today. And also we'll have a short, probably about 15 minutes on the data analytics and data collection. As you already heard from speakers this morning, or probably also in the afternoon, there are some discussion about how to get data collected, sensors, how to get sensor data collected, shared, and also put together in your model and help your model get better and better. And that's part of actually the whole pipeline we are building through the digital twin paradigm. And next we'll have some practical case study. That's a study we started, Igloo and Dr. Tedeschi, they have been here helping us to, they're actually working on that physical facility. And we are trying to help to get the data collected and analyzed on our own. It's still an ongoing project, but we do collect a list of commodity hardware you can buy. Most of them are from Amazon. I think you get some from other places, but we do have a list, like a shopping list for all the hardware we have. We purchased and for this research project, and we hope that will help some of you get started. Just that's some good resource, and you can get started. So finally, we'll have probably 10-15 minutes for question, and we can wrap up the tutorial. Before we get started, this was supposed to be a hands-on, hands-intensive, or I'm not sure how you say it. We call it hands-on sessions, but depending on your familiarity with the Python programming, this might be hard. I don't expect you all to learn how to do all the programming just in 1.5 hours. It's not practical, but I hope this will give you some head start, get you head started into programming, because doing programming, it's kind of a way you can communicate with computer. Now with the ChatGPT and all the other tools, you can communicate probably in a different way, but programming is give you the language that the computer speaks and make you communicate and more, probably more efficiently and effectively when you want to do something on a computer. And Google Cloud Theory is a tool that a lot of data scientists have been using. And if you want to install things on your local laptop, you can have a Jupyter Notebook or Jupyter Hub installed. If you know how to install Python, install this tool will be almost trivial. Just 2 command lines away or button clicks away, they will be there. You can run your Python script on those for free without paying anyone any money. You can just directly run on your computer. And with all the open source Python libraries and modules ready for you to use without any fees. That's a beauty of this open source, open science community. So for this Google Collaboratory, I put a link there. I probably needed to, I better share this somewhere, but it's okay. The video I'm putting there is showing you how to get you started. When you go to the Google Collaboratory, if you have Google account, just click search Google COLAB, Collaboratory. So that's started as a Google research project, but now it's almost the default platform for data scientists using this Google platform, cloud computing platform, to do anything relevant to data science, big or small. If you want to run big projects, it's fine. Prepare some money and just pay them, and they'll give you resources you need. If you just want to run it for free, it's fine. You don't need to pay a single penny. You can run it for free for 1 hour at least on their GPU and TPU. These are very fast processors that you can leverage for research. Okay, let's get back to the slides. Okay, so that's the platform we want to use, Google-based, Google. It's a Python-based platform, so you can use a Google platform, cloud-based platform. You can use your own laptop just to run things. That's all we need. Actually, it's kind of interesting. The reason we are fully equipped mainly because of Python ecosystem. It has all the tools you need for a lot of things that you can even think about. So for this particular workshop, you saw the tutorial, the focus will be smart farm and the farmer future. That's a larger, what we call big vision that we have in our mind, and we started working on this project. We are working with people doing, say, cotton field, somewhere in Corpus Christi. They have a lab, and they got sensors setting up. They got drones flying around collecting data. That's something we're working on as well. We're also working with Dr. Tedeschi's team at ASAS-NANP and install sensors in our somewhere. I'm not sure exactly the particular facility name, but it's in our beef center. We do install sensors and mostly cameras to get data connected. We are starting doing all the data collection just recently, and we are currently working on this platform on our end just to set things up. So particularly for the precision livestock farming, as you can imagine, the whole process is mostly about data collection, data curation, modeling, and finally gets to the decision making. So this pipeline, it's always, no matter if it's a digital twin or just data science project or just your animal science project. So the beauty of digital twin, this concept, is that you want to get your model and your data and your real world data, sensor data synchronized. You always want latest data available and get your data, get your model updated, get the latest results. So then you can use them in production, not just use it for theoretical research, analyzing some historical data. You want to make some forecasting, make some predictions. So that will be really powerful for farmers. With some models, with some real world data, they can keep track of how their farms are going. Right? They can link to the market and can directly get numbers, make predictions about the profits they can make. So essentially, we have these 5 parts that I think will be more or less like what digital twins are mostly about. So starting with livestock, that's your farm, that's your research lab, and you get the your animals there. You push all the sensors necessary. Sometimes intrusive sensors might be harmful or bad for animals. Sometimes we have big tanks like around the necks. And sometimes we just put some towers collecting data. There's different ways to collect data. And also next is about some tools that we want to utilize, like a GPS system, RFID tag, and also drones. Some of you probably already got a license and to fly drones. Sometimes we probably don't in a rural area, but sometimes if you're getting into a suburban area, you need a license, fly drones, collect data that way. And then you can also install remote sensors. separately, depending on where you want to put them. It's depending on the also size of the farm you're managing. And also you have worry about automated feeding system. You want to measure how much and when, etc. You want to get the data. You want to get the pattern recognized, and you also want to control that. That's the feedback loops that we'll be talking about later on. But for what I'm trying to cover today, we don't have a feedback mechanism yet, but it's in the future. The idea is that you get your data collected from your farm, you make some modeling, make some prediction, and this prediction can help you to go back to control your farm. There's some mechanism for you to do some, say, change the replace the water or feed of animal food for your animals, etc. And then you have data curation. This data curation is it's not just for your, probably sometimes you can go even bigger, not just for your farm. For the research community, you can share your data. This curation could be the community share, community platform for sharing data and exchanging knowledge and experiences. And it's pretty common in many other fields, if you know that. And also, for those of you who have been doing data science in animal fields, there have been, many platforms you can share your data with others. And then you have data analytics. Based on the data you have, you build up your models and then learn from other people's work, assuming that model might be applied to your data. If it's not working, modify the model, make it work for you. That's how we do all the science, not just for animal science, many other science, we do it the same way. And finally, you want to have the decision-making. That's the ultimate goal for all this work. We want to use this model, this data-driven model, to give us some information. And based on information, we can make some smart choices. So I already mentioned it. So for the digital twin, the physical twin, these are two different objects. Digital twin, more or less, you consider a digital replica of the physical twin, but there is a data connection between them. So the physical twin is a real physical farm that you have been studying. The digital twin is the one we want to build based on the physical twin. So in part 2, I think we are okay. We're not so further ahead of time. Before we get into part 2, any questions? Okay. So we don't have time to go into details, but get your hands dirty, but I'll go around table after, we finish some of the lecture slides, and then we can get your hands started to run some testing cases. So part 2, I'll talk about digital twins and applications. So digital twin is, as I mentioned, is mostly about how to connect a physical object or digital object and get the data synchronized. So there are 3 major components, and we want to make sure we have those essential components. First one is a representation model. You need to have some representation for your physical object. If you have farm, you need to have some virtual object created in your digital world to represent the farm. So then how can you refer to a particular animal without a physical, virtual quantity refer to the animal when you need to grab the information? And for you to synchronize the data between the virtual and the physical, currently we're just getting the data one way, but in the future, if you have some feedback loops, you can always go back to change the physical quantity, even for animals. If you have, for example, if you have some feeding mechanism, and with this controlling feedback loop, you can, based on the eating habits and all other measurements, you can control how much food you want to feed into the particular animal based on the health condition and other requirements. So it's a representation model that will be more or less like your virtual self, kind of like this. You're building a virtual animal and a virtual farm. And the simulation model is a model mostly focused on the virtual side. So after you get some data, consider we already have the state of this animal already taken like a snapshot. We know everything about the animal at this particular time, this time slice. If you know numerical simulations, when you simulate, how the rocket fly up to the sky and how things are moving and how the fluid is spreading around this certain environment, you go this step by step. You know that everything happens at step time t, you go to the next time, t plus delta t. Continue doing this. That's how you do the simulations numerically. It's kind of similar. Now you have everything about this animal, this farm, assuming, if we have, in the ideal case, we have all kinds of sensors we need. We can buy all kinds of sensors we need, right? We can measure everything we need. Actually, virtually, it's all we need to do is just figure out how to evolve all the state from t to t plus delta t. That's what the most modeling is mostly about, right? But in most cases, that your model might not be directly utilizing this time variable. We call it implicit variable. But when you do any predictions, anything in the future, you are playing with this t hidden, called implicit variable. So simulation model is trying to bring this current status and also historical status of your object. Could be a farm, could be animal, into the future. That's a simulation model. Now, this cyber physical system is trying to connect these two. Cyber physical. Cyber means digital, virtual, and the physical is a physical. This cyber physical system, it's CPI system, has been there for many, many years. There have been a lot of work in engineering just to study how to get the cyber physical system working for different physical systems. So these three components are essential for real digital twin. If you are someone talking about digital twin without counting these three parts all together, there might not be a real digital. It's probably just a digital copy, and just focus on the simulation or focus on just a representation. But you need something to synchronize this to make this like a digital twin. So that's actually what we are doing in our school. When I joined our school, actually back since the Department of Visualization, when I first joined the school, later we started a brand new school called School of Performance Visualization and Fine Arts. And a lot of students in our school have been trying to develop games using Unreal Engine. I'm not sure you guys, you all heard about Unreal and Unity. Those are game engines people use to develop 3D games. And Epic Games, it has pretty famous recently because of the lawsuit against Google, and also because of the stock price. I don't know if you are buying stocks, and Epic Games has there are also some other game companies. Because of the pandemic, everyone's staying inside. Kids that just playing games on a daily basis, even adults, sometimes you get there. Now, the thing is that the way how they design game is mostly focusing on entertainment. That's what we train our students. Hey, do it. And we teach them, in reality, we teach them how to get your players, I'm not sure it's the right word here, addicted. That's the whole purpose. Just like for some food, you design your food to attract your consumers, right? So then they get addicted to your food, so they keep eating your food, your brand. Coca-Cola and Pepsi, they have a different taste. It's kind of idea. There are different strategies to attract certain group of people to play certain group of certain kind of games. So that's what I've been teaching, but they can do more, right? They cannot just, gaming is not just for entertainment. This kind of gaming technology is now probably the high tech. It's not simply just someone kids stay there, just tell you how to move your mouse and do something this and do something that. Gaming business now is driving the current development of AI technologies, visual computing technologies, and a lot of things that with the gaming behind it. It's a huge market, has a lot of capital, and it's a big. So this game is called I believe it's called a Meat Factory, and you can probably find it on Google. And it's developed with Unreal Engine. It's photorealistic 3D game. It's just like with all the AI technologies, all the 3D model building technologies, the things in the game now looking so realistic. And there's also a project under for the Unreal Engine that's called a MetaHuman. You can generate human figures just like a real person. You can do a quick search, and you can see how scary other technology nowadays with all this gaming business. This could be used for building digital twin, but as you may imagine, it's time consuming. There's no one, here. I assume if you are all doing animal science, you don't have time to do this kind of 3D model. But this could be the visual representation for your project. If you have the money, you have the resources to develop it, this could be the front end. But today, we'll definitely not do this. And we'll have a web-based interface, more or less like giving you some understanding about how the visualization could be done in a different manner. But that's the ultimate visualization representation you want to have, which is photorealistic. Oh, there's a reason. So one of the major reasons that why photorealistic is so important. Think about self-driving cars. people have been, Tesla, if you have a Tesla, you are contributing data for Tesla to train a model to help you drive your cars. But the problem is the majority of the data used to train all the self-driving cars are from virtual environment. Why? Because accidents are happening, but you don't have so much data about accidents. Those are corner tests that need to be trained. Otherwise, how can the machine know what accidents will look like if they don't know, have never seen the data? Just like you tell kids some bad things, if they have never seen them, they have no idea. They just know the words, and that's it. So being photorealistic within this kind of environment, you can use this generated 3D scenery to train your machine learning models, which will be something really useful, which, it's not a primary topic today, but that's another big application for photorealistic 3D high fidelity model like this. Okay, so we finished the representation model. Remember, we have 3 components, right? If we talk about digital twin, what's the first one? Representation model, I just covered. You need to do simulation, and then you have cyber physical system to connect them. That's, like a dumbbell, you have 2 parts, you have a data link connection. That's a digital twin. So for the simulation model, there are 2 big paradigms. First one is so-called a theory-driven model. That's people here, I believe in this community, we call it mechanics, right? All those things that you already have something very studied, or I'm not sure how you call that here in this community. Mechanics, science, engineering driven, I'm not sure. But you have some basic understanding about biology, and you have understanding of physics. There are like energy conservation or conservation of mass. Those are fundamental laws you have to satisfy if you do have a contained environment to do those. That's a theory-driven model. You already have the governing equation, and you know how things are changing. It's mechanical. It's more, not talk about living things. We're just talking about a mechanical thing. You have a fully controlled mechanics about how things are working. But with that, you have governing equations. You can just discretize your continuous equation into a discretized form. Then you can put in your computer, and then you can write your models, it will run and give you some output. So that's where you do the theory-driven model. Second one, paradigm. I would call it paradigm. It's not an algorithm, it's just paradigm, how you do science and do research. It's a data-driven modeling. And here I'm focusing on supervised learning mainly because when you do this training, all you need is just someone give you a neural network, or you can define your own neural network. That's a structure. Consider it a mathematical structure. All you need to do is just apply all the data into this manufacturer or whatever, this mathematical concept or mathematical structure with a label. The reason you need a label is you need a label to tell when you train your model if this prediction, the model is giving you the correct result or not. It's keep teaching that with the data. After that, you get a model generated. This model is nothing more than this structure to the left, something like that to the left. It's just connecting nodes and all the parameters on each node. So put them together, you can have a model. Model is what? Model is nothing more than a function. It's just a function. If you're writing program, it's a function. It's mathematics, it's a function. From every sense, it's a function. It's model, it's a function. And now you get model trained. If the model satisfies certain criteria, so already you know the error is already very small. Then you can start using the model and put in the new data there. The model can make some predictions for you. Now the beauty of this data-driven modeling effort is that you don't need to know anything about physics or whichever governing equations. You don't need governing equations. All you need is just someone smart enough to give you this mathematical structure, and you just feed in your data. As long as your data is correctly labeled and the quality of data is good enough, you can put it into a mathematical structure and just try to tune all the parameters. That's what, of course, that's not your job, that's a computer's job, right? Your job is to figure out what kind of data matching my particular application. I just need to figure that's why data is so important. Data is gold, data is the oil in the next wave of industrial evolution. So current, ongoing, and the next, right? So that's why every big companies, they're so eager to collect data. With data, you can do a lot of things that you cannot even imagine. Think about ChatGPT. So the beauty about ChatGPT is the data it's utilizing. The algorithm has been there, developed by Google many years ago. People have been using it for many other things. But this company, they spend money, collect a lot of data, they train a model. Now just look at what we have now. So now I talk about number 3, cyber physical system. So for number 3, you are most concerned about what? Data connection. You need the sensors. Some engineers need to be there and design the sensor for you. You might think about, okay, we can probably just put some human there to do the counting, but we talk about automation here. We can send human beings, farmers there to help us collect data, but we want to automate things. That's the reason why we want a digital twin. This digital twin help us to automate the whole process. So the sensors, most of them, I would say majority of sensors is trying to convert physical measurements, physical quantity into some electromagnetic signals or whatever signals. Those signals could be decoded into numbers, and these numbers could be stored. That's how you do the sensing. You have a sensor, convert them into electromagnetic signals, convert them to numbers, you save them, you collect them, you share them, you use them. But are you really dealing with data yourself? That's kind of interesting, fascinating. What is the data here? The data actually already converted into different domains. That's all. When you're measuring, say, medicine, right? You want to know the density of medicine, in a farm. You set up a medicine tower, or you have some wearable masks, and you can measure them. But everything turns into electromagnetic signals. That's not the raw data you're taking. But that's what we have. So all the sensors, almost all the sensors based on this EM, electromagnetic signals. There are some mechanical sensors you might use them, but finally, when you try to analyze the data, everything needs to be turned into numbers, digitized those, and those will be converted into bits into your computers. That's the data we're talking about here on virtual. What's the real data? I don't know. How can you define a physical data somehow? You need some form for data to exist. So the data transmission is important because when I'm not sure how we heard about edge computing. So edge computing is that when you install your sensors, you install some, cheap and very efficient, lightweight computers. It's called edge computing. So you want to put your computing power close to your sensors, close to your data. So you don't need to move the data a lot. All you need to do is just get your small computers like Raspberry Pis, or sometimes you can have retired phones you can attach to the sensor, and the sensor can collect data, and the phone can help you send the data or analyze the data. And then you don't just send all the raw data through the network. You can just send analyze data. That's much, much cheaper. And also, if your farm is a bit further away, and you just set up a network connection, the bandwidth itself is not free, even though it's getting cheaper and cheaper. But if you want to have unlimited 5G connection, it's almost I'm not sure it's will probably still cost you some money. So the idea is that we collect data, we analyze that a little bit. We don't want to, we still save data locally. Just once in a while, go back to check. We definitely want to save this raw data just in case something goes wrong. We still have something to refer to. But the rule of thumb is to, reduce the dimension and try to analyze data a little bit from your source end, and then you can transmit to the processed data, which is much lightweight. So again, after you get information, you have some models, and then you can get it back to the system. So I'm talking about cyber physical system. I'm not talking about the models. I'm just assuming, you already get your data. You made some decision and say, hey, I want to do this. You send this information back to the sensor side, or there will be, I'll call this hardware side. There will be some motors, convert this magnetic signals into motions, and this motion can do something. I'll open up the gate, or do something physical. That's you change your decision to the physical world. You don't need to go there. That's why all the switches, remote switches, you can open and close the gate and do many other things. You can even click the button and get the drones flying out automatically, and the drone can fly back to the charging station automatically without you going to the field. It's not science fiction anymore. It's already people have been doing that. So there are many things we can do with this cyber physical system. And there's a lot of research and also a lot of startups currently working on this, because it has huge impact on our society and next generation of farmers and engineers. So for the cyber physical system, you can consider this like a tiered application, a tiered like a structure. At the very top is application. It's whatever you do. It could be manufacturing, public safety, engineering applications, and agriculture applications. Below that, you have so-called middleware. The middleware is trying to understand what your application needs and then translate that into some shared, resources. For example, the resource management that, it doesn't really care if it's from engineering application or manufacturing application or agriculture application. You just need to know how many computers you need for me to do this, or how many cameras you're managing, and how much data, what's the data bandwidth you need for me to transfer this much data to there. So it's managing the resources. The same goes for AI machine learning modeling. Give me a video stream for the machine learning model, doesn't really care if it's an engineering application or agricultural application. It's your decision on the application side to decide, okay, I want to detect a cow. I don't want to detect this particular, screw or nuts or whatever, right? So that's something make it really interesting that, you can nowadays with all the software and hardware platform, you can create this shared middleware that could be utilized and for different applications. That greatly makes the whole computing and also storage application, network applications very, very efficient. Below that, you have the gateway and connectivity information. Those are also, you're working on animal science. You can still use the Wi-Fi as I use Wi-Fi. It's the same Wi-Fi. So that's also make it very easy to share all these resources. That's a gateway connectivity information. Then below that, all those are devices. You can use device to measure things you want, and you can have motors. But whatever motors will be doing will be controlled by layers upon layers, and finally determined by the application and your goal for your application. So this kind of structure makes it easy to separate different concerns, which is very important for engineering applications. People focus on application, they focus on application. Don't need to worry too much about whatever hardware is designed. I have been working on computer science application for many years. I don't even know how the wireless router was designed, right? I never needed to worry about it. As far as I know, there is a 7-stack layer. This is a top layer, and the second layer, other things I need to worry about. Everything lower layers, that's something engineers and electrical computer engineers or computer science engineers need to worry about. So that's how we divide our tasks, among us in our society, and we get things moving. Everyone doing their job. And that's how we move nicely forward. So, as a part of the effort at our digital twin lab, we are implementing a reference model for building digital twins. We're not saying, we're not the team to do this. We're not going to say, our model is a model everyone needed to use, but it's just something we want to get started. It's partly for training purpose. I have students from, visual computing and doing all the game design. I have students from computer science, engineering. I have students from animal science working with me all together. We need something, some standard internally. So we agree upon certain structures, data structures, so that everyone can talk to each other without, arguing about which format of data we want to use, etc. So we came up with this reference model, which is very, very simple, at a very high level. But if you want to go to lower level, it's getting a bit more complicated. That's what I'm saying about separation of concerns. I do have computer science students help me write the programs, Python, C, C++. I have my students from the visualization department helping me working on the Unreal 3D visualization work. And I have students, from animal science, like Igloo, working on the animal domain stuff. So we can get a team working together through this kind of reference model. So the physical space is nothing more than just sensor and the physical objects. That's generic. That's a part we don't worry too much. If it's there, it's there. We install it, we can use it, and that's it. We don't worry about. As long as we have the application programming interface provided by the manufacturer, we can directly use it. Some of the hardware you purchase, for commodity software, they want to make things easier. They have their own cloud-based resources. You can just log in there, click buttons and just find the link. You can use the link to download your video stream or other data sets. That's the way how the commodities hardware are working. Make it easier for sharing data using cloud-based resources. So in the digital space, it's the things we are working on currently. First, give me a cow. I needed to build a model for it, describing the status of cow. Of course, I can model every tiny cell of that cow theoretically if I can, but we don't need to. So we just based on the sensors we can, and also everything, all the domain scientists tells me, say, hey, all the domain scientists tell me, say, hey, Jian, we need this and that. And then we decide what kind of sensors we need to purchase to measure this kind of stuff. And then we don't need to build a cow from a model of cow from cells level. We just say, okay, I want to know the weight, I want to know the height, or other characteristics. This is called feature engineering in the machine learning. You can take a picture of a cow. Based on this picture and based on the reference, you can use your computer model to roughly estimate the features of the cow. Again, some of the features probably is not so fine-tuned enough, so then you cannot use this for 4 or 5 numbers to tell to identify individual cow. But if you go to a certain level, if you know the patterns, all this, how to call the fur and also other information, you can tell the difference. That's how your face ID is working, right? As long as you scan your face at a certain level, you can tell the difference between one person to another person. If you can extract the information from this, whatever you get from the sensors, you can identify your cow. Of course, like RFID, it's one way to do it. To give you another dimension, because you needed to physically inject something or a sensor there. You want to measure this information by identify individual cow. But there are many other ways. Computer vision-based technology help you do that. Just like Face ID, you can use the same technique. But for cows, it's probably easier in some cases. Of course, if you have those tools already set up. So that's a digital object that you want to create for the things you want. As I mentioned previously, for you to build this simulation model, you want to know the status or state of the object at a certain period of time. Then you can make predictions, t plus delta t plus delta t plus delta t. So that status, that state, needed to represent this object. You might not have that very comprehensive list of things to describe this thing, but for the things you're interested in, you need to have all the variables, all the data you can to collect them. And then you have your models, and you can make predictions. The prediction can also give you some information about the system. And then it's you, currently it's you need to make the decision. But in the future, think about this, in the future, some AI, which have been trained, the AI model could be trained just like driving your cars. They can make decisions for you for the whole farm. It's doable. Even now that's doable for certain, if your farm is designed a certain way, it's definitely doable. But again, now it's still a decision for farmers to make. What we need to do for certain, if this cow is sick and this kind of stuff. But assuming in the future, if you have all the information about this cow, if you send all the data you collected to some expert, they can probably tell you what kind of medicine you can give to the cow. And this could be done theoretically. At least, for now, it's not a science fiction anymore, but it seems to be getting closer to us. So there are 2 directions of data streaming. One side is the data going from the digital space to physical space, digital space. That's how your sensors are doing. Your sensors are collecting data. On the other end, your digital space can send the information to the physical space, providing instructions what the physical space should look like and what the actions should take. That's a cyber physical system. So the other kind of applications that I have been working on, some of my colleagues at ASAS-NANP has been doing work on smart cities. Probably heard recently that Singapore, they have built a whole smart city for the whole city. Singapore is a relatively small country and it's able to do that. For some big countries, China, US, you can do it for a small area, but the large scale is still hard. So for the smart city scenario, you can build a smart city containing all the information about the pipelines, everything. Think about that. How easy someone can dig up the pipes, the cable, and it destroys the connectivity information or gets the water burst out, because of the lack of information. And that's actually doable with all these so-called BIM model. I'm not sure you heard about it. It's called a building information modeling, BIM model, and there are also similar standards in different communities for new buildings. I'm not sure about other states, maybe. I heard in Texas also they're requiring all the new buildings coming with the BIM model. So the BIM model contains a lot of information about the building. If you build this house, they will need also the materials for everything you use in your house, and also the pipes, and also cable, how the things working. You get everything inside this BMMO. But of course, you need someone dedicated to keep maintaining the data. Otherwise, it might not be so useful. Sometimes it might be have some negative things if you don't maintain your data up to date. So this video I try to show you all, if you are a big fan of NVIDIA, this GPU company, and you probably haven't seen this. So this is
welcome to BMW production, Jensen.
So this is a digital twin created by the BMW and also NVIDIA in collaboration. So they're building the whole manufacturing process. This whole workshop, all these are created virtually. It looks like a real, factory, but it's everything. Everything inside this is just virtual, just like in a game. Okay. Oh, I'm sorry. Let me go back to the previous slide. Okay, let's just continue playing this one. I just want to, slide shows here. Okay.
Put them down there.
First of all, I'll get you a taller one, but there's
So what they are doing here is they're using
it's
gesture contraction devices. So that's all the information about how the body is moving could be
digital humans are trained with data from real associates.
and I can control all the
You can then
robots.
use digital humans.
Think about this. With that information,
test new workflows for worker.
the way how to train robots to do things will be much, much simpler. And actually, that's what people are doing with the robotic
7,000
arms.
people.
They can follow you on
Your
your
space with many robots designed to make their job
So
easy.
think about if you want to precisely control something.
You're right, Jensen.
And you want to teach it, run program each piece, each thing.
With NVIDIA,
but if you have a human body,
BMW is deploying
if the model can
intelligent
trace your movement to a human body, it can generate this
material flow in all production. This agility is necessary since we produce 2.5 million vehicles per year.
All these are just virtually created in the virtual environment.
Synthetic data.
So, okay, so I'll share the links, and so you can watch that later on, which is quite amazing. As I mentioned, game design and all the tools developed for game design could be used for entertainment, but could be used for many, many other things. Very, very, cool and helpful for our society. So before we move into part 3, any questions so far? Go ahead.
BMW, is there something which could be saying we can improve our efficiency to redundant, meaning that we improve our efficiency so much that we become redundant?
That's what's if you are CEO of BMW, you probably want to fire everyone working in the company, just use AI, right? You can save a lot of money, even though the initial cost now is for the robotic arm is still not cheap. I think for the workable robotic arm, it's about $70,000 to $100,000. But consider how much you're paying for your worker. You probably want to just, if you can train the robotic arm to do the things the worker can do, you definitely want to use robotic. It's 24/7. It doesn't. You just need to give it, energy, electricity, and just keep going. But no, that's not the question I want to answer here. It's probably, we are recording everything, so it might be putting me into trouble. But I can talk with you, afterwards. And any other questions? Okay, that's great. So let's move into part 3. So about data collection analysis. So I give you some overview about the digital twin and what could be done and some applications. Now we get into the real scenario, how we want to do the data collection analysis. So that's a part of focusing on for our digital twin project. Before getting into that, because in the title of my summit, this talk, they asked me about the title. I put in big data analytics, but I needed to talk about it. Even though the data we are collecting, except the video streaming data, all the other data entries cannot be really categorized as a big data, because the volume of data is mostly about, for example, temperature and movement and XY position for the cows. those are not big data in a sense. Big data, we're talking about terabytes, now even petabytes of data. That's huge. But there is a different characteristics for big data. When people say big data, the volume is big. That's a size, how big it is, for example. But that's relative. There was a hidden variable of time there. If it's like 10 years ago, if you talk about terabytes, it's huge. But now terabytes, it's okay. My laptop has 1 terabyte of hard drive, and also you can, petabytes. Those are almost unlikely. 10 years ago, probably 15, 20 years ago. But now people talk about exascale computing. That's 1,000 petascale. So because the technology is evolving so quickly, so the volume itself is relative. So when you talk about size, as long as there's something your laptop cannot easily handle, you can call it big data in a sense, because you cannot easily handle data, you have to use big machines. That's big machines associated with big data, right? And the velocity here is about the speed. Sometimes you want real-time data. That's why 5G, 6G, people talk about next-G and 6G are coming. They want real data. They want real-time data. For self-driving cars, you definitely want getting information quickly and as soon as possible. People talk about V2X, vehicle to everything, and vehicle to vehicle, V2V, and V2 infrastructure, V2I. When you want to get a signal from the traffic light without seeing the light, that information needs to be coming to you quickly without a lot of latency. The reason why 5G is so important is that it's not just bandwidth itself, it's about latency. For 4G and also Wi-Fi, latency about 1 to 10 milliseconds. But the 5G is 1/10 of that, or even smaller. So the latency here is a delay. Even before you transmit anything, you need to establish the connection between your phone and the tower, right? The time delay to do that, it's a fixed delay. Whenever you start to establish this connection. So velocity here is, for different applications, the velocity could be related to the latency or could be related to bandwidth. If you have 1 gig of data want to transmit it, the bandwidth is probably a big concern. But you have 1 byte of data, but you need to send this quickly back and forth. Every time if you have a 1 millisecond latency, that actually make your transmission very, very inefficient. So that's velocity. You want how fast your bandwidth is, etc., or how low your latency is. You have a variety here about different kind of data. For animal science, depending on your fields and what kind of research you're doing. And you might collecting data from weather stations, from your sensors installed somewhere on the farm to measure the methane, carbon dioxide, and all other things on the site. So it's your choice, it's your research. If you want to increase number of data, type of data you want to collect is fine, but your model might not be using that many types of data set. You probably want to just focus on certain type of data sets. So that's veracity here, mostly about accuracy and also validation kind of related, which is true for almost all the data. You definitely want your data to have less, the data you're collecting with less bias, with less variance, and as focused and accurate as possible. Finally, values, this means how this valuable your data sets are. Sometimes you collect tons of video stream of your farm, but actually it's not so valuable. In the sense that you don't need that much information. If I keep a camera here, with this everyone inside this room, the information I'm getting is just get a static image of the background with people moving around. The information I'm getting is not that much. The extra information. That's like relative is entropy. If you talk about physics, that's entropy. That's a complexity of your system, right? You want your data to be valuable. You don't want to spend tons of money to install sensors and measure something not so useful for you. So there are different types of big data analytics you can do. This is more or less like different ways of different types of data science project you can do. You can just collect the data and just create some summary and give some statistical reports. That's already descriptive analysis. Tells people what the distribution of data will look like, and what's the mean and what's the median, all those kind of information, statistics of the data you're collecting. That's already built for certain data science project. You don't need to build up a model for that, because sometimes people just look into those kind of information. That's a descriptive analytics you can do. Then predictive means you need to make some models, you need to make some predictions, and that's different type of data science project and a different type of big data analytics you can do. And then you want to, have some prescriptive analytics. Not only you want to make a prediction, you want to see what you can do to change the predicted results. You need to understand a bit more about the things you're measuring, you're doing. And then diagnostic, mostly what will happen. That's something you needed some domain knowledge. You needed to get back, get your data, pick up your textbook. You probably already forgot. You learn in your undergraduate time and just trying to figure out what's going on there. Why this data is happening this way, etc. It's a common for almost all data science problems, but it's the same for big data. I just want to emphasize here, every time you get data, you need to ask yourself kind of questions. What kind of analysis I want to do? By doing that, you'll have different set of tools. For number one, for big data, probably cannot use Excel, but some simple, Python package can do that for you. Pandas, Dask. There are many different tools can get that first one to you quickly. You don't need to learn how to use TensorFlow or Python to build up machine learning models. That's sufficient. But if you want to answer the next three questions, you probably want to learn how to do the modeling, how to do the data-driven model or theory-driven model, etc. How to do data simulation. Many different things will be involved. For big data analytics techniques, today we'll mostly be using machine learning, deep neural networks. But you can do data mining. Data mining in the sense that you want to see how data distributed. Do they have any patterns that you can recognize, even though you don't know what they are, but are there any way you can see the patterns? It's called a clustering. And that's so-called unsupervised learning. That's mostly data mining, and also for machine learning, you can do supervised machine learning, unsupervised machine learning. You can train a model to generate regression models, and you can do some statistical analysis. You can also do some predictive analysis to see how things will be happening in the future. All those require some kind of modeling. You need to have some strong grasp of statistics. Sometimes you even need to learn linear algebra to do this kind of stuff. But in most cases, application developers, you don't worry too much about math. Even though I'm not saying math is not something you have to. It's not something you don't need to learn, but sometimes we don't need to know all the details for the math on the mathematical side. We know what that algorithm is, what the algorithm is doing. We understand the input and output. That's should be sufficient for most of the applications. That's what I tell my students. If they are developing, if they are not developing, machine learning algorithms, you don't need to worry too much about your mathematical background. You can still do a lot of very good science. So sometimes, there is an impossible syndrome, right? Some students are kind of concerned. Hey, Dr. Tao, I enjoy doing all this, but I don't have a strong background in math and statistics. How can I do anything? I say, now the models, machine learning models, and also the tools are there. You need to have some understanding. You don't probably not to the details. For example, I don't understand how Fortran models work, but I've been writing Fortran code for many years. Why do they need to know all the details to do the kind of science? So that's basically make you probably feel a bit more comfortable if you're kind of scared of math, which is kind of common for a lot of students in different fields. That's especially the problem I had with our students who are doing game design. But again, you do things you're most good at, you're most interesting, and that doesn't really prevent you doing something fabulous. Collaborating, and that's the thing. That's the way to go. So we talk about data collection and analysis first. So to collect data, you need a sensors. This is a type of sensors you might be seeing. Probably most applications in engineering, you'll see a lot of sensors, a lot of pressure sensor, temperature sensor, everything you can feel, you can touch. You can always imagine there could be a sensor already out there available for you to just text a sensor and do some measurements. Now, it's another concern is about the price, sensitivity, a lot of these things that will be depending on your application. And the most useful sensor to me is this camera. You can have a thermal camera, have an RGB, regular camera, called RGB. We would call it RGB camera. Thermal camera is mostly infrared camera. You can measure infrared bandwidth band, and you can roughly you can see things. When the visible condition is not so good. And streaming videos from the cameras will be, as I mentioned, it's very useful, but it will require it requires a lot of analytics to extract information from this video streaming. People call this more or less like going from computer vision to semantics. You needed to extract information out from this. All the AI tools now, there are a lot of AI tools are focusing on doing that. If you want to upload a picture to Google and ask Google to search it, generate some phrase based on that. There are some tools now that you can upload it and generate a phrase describing what this particular image is about. So that requires a lot of machine learning effort. You need to train your model not only with images itself, but also with a lot of language models. So it's like combined the Martin model and the model fusion technology need to be enabled. So that you can combine language model with a computer vision model. But that's kind of beyond what we're doing today. We try to primarily using this streaming video to do the tracking and monitoring. Think about it, you don't need to, if the model itself is working, assuming, you don't need to install all the GPS tags for all your cows. You can use probably install a couple cameras, depending on how your ranch is, how your farm is, you can install multiple cameras help you to do the detection. Not just one, you can have multiple cameras working together, they can coordinate, to different fields, they can figure out which one is overlapping. There are many ways to do that. So monitoring the behavior of animals, sometimes you can see if they have some problems because it's too hot outside, which happens nowadays. We have animals standing outside in Texas. We don't have any shade for some of those, which is kind of, they get some heat stress. And you have livestock tracking. Of course, again, it's depending on the size. And when you're getting further away, you're getting smaller and smaller inside of your view angle, and then you won't be able to keep track of at some point. But you can install multiple cameras, and there are many ways, other ways to do that. For example, you can fly a drone and help you to do the scanning of the field, etc. And also safety, security, that's people have been using cameras for. Security cameras are there for this purpose, and then you can also assess their size. The size could be assessed now because you can do not only, we call optic detection for your cow, you can also do the segmentation. Doing segmentation, more or less, you can draw the profile of this cow and you can roughly estimate the size. It's already, people have been doing that, and it's already used by some people to estimate the growth of certain animals. As long as you can keep track of individual animal, you can do that with computer vision technologies. Also, there are other things we can talk about. You can remote farming and research and training could be done also. You don't need to send the students there physically. You can use this for training purpose. So now, assuming you have all the sensors installed, camera installed, the next thing you worry about is get a sensor transfer, data transfer. That's actually a lot of work done by Igloo. It's just to Igloo methods from from ASAS-NANP. We spend no time just setting things up. Installing cameras is one thing, but you need to figure out how to get network connected. Wi-Fi is working fine as long as you have some wide connections, so you can connect to your router, you get everything out. Most of the sensors nowadays are IP sensors. You can get the they can automatically get your IP from your wireless routers, everything is connected, it works perfectly. But not all the sensors work that way. Some of the low-end sensors, like temperature sensors, some pressure sensors, they might need like Arduino or Raspberry Pi or even a phone to connect to it. Then they can do something. So there are multiple ways to connect your data. You can use a Wi-Fi, cellular data, 4G, 5G. Now you have 6G test bed somewhere. Ethernet, if you have a network connection, you have Ethernet, just cable, regular cable. And then you have Bluetooth, and there are ZigBee. Those are different protocols that you can connect to. And different connectivity have different, pros and cons. For example, if you want to connect to a sensor further away from your base station, you probably want to consider some other, say, at least for 3G, 2G, those can go a bit further away, several miles maybe from the tower. But for Wi-Fi, even in a big house, you need to probably buy extender. So Wi-Fi extenders, right, to cover the whole house. So Wi-Fi is not very big, especially now. Wi-Fi is getting from 2.5 gig to 5 gig. The high frequency you have, less formidable the signal will be, because it has high frequency, it has a low wavelengths. It cannot pass around your building easily or walls easily. So with all the new Wi-Fi routers, your signals might be just limited to probably just your house, or even sometimes you can get further away with an extender extension. How to call the extension, Wi-Fi extensions. There are also other low short distance communication like Bluetooth, and you're probably all familiar with that as well. So there are multiple ways to connect your data. After you get connected, this is a low level protocol. It's the same for all the communication, and it's just like which one you want to pick. Each one has different price tag, and each one has different things you want to consider. But that's all the choices are there. You can just pick the one fit your needs best. Now, on the server side, assuming you have sensors there, you have network connection already figured out, you want to use the Wi-Fi, good. Now, how to collect the data? This is probably one of the best things I found in the last 2 years. We have been trying to experiment different things. This MQTT is kind of really amazing piece of software, started by IBM, as that makes the code open source and is used by many companies for sharing real-time streaming data. So all you need is just set up a server. It's a server can be set up just as simple as just one line. That's it. One line of code, and just click it, or you can do it probably if you're on a Windows-based system, you can probably click a button and set up your server. So server will be there. What the server does, it will be waiting for all the incoming data. If this incoming data is sent into a certain topic, so there is a key concept called a topic. It's just like a news group or mailing group, or mailing list, or Google group, right? You create a Google group, say animal science. Okay, now you have a topic called animal science. You can create a topic. It's just one command line. I can want to create this animal science topic. And everyone send a message to this topic will be collected by the server, will be broadcast out. If anyone subscribe to this server, will get this message. It's like a news group. You probably some of you have used RSS, if you use that as well. There are also Google group, it's working the same manner. It's called a subscriber, publisher, how to call there's it's not a paradigm. I think it's like a model. I'm sorry. It's called a publisher and subscriber model. And a lot of Web 3.0 or 2.0 services working in the same way. And also the robotics controlling system, ROS, called robotic operating system, ROS, which is very popular in robotics community. It's using a similar mechanism for communication messages between different devices. But this one works on the internet. And someone could be sending me a message from Europe, as long as I give them the access to the server, they can say, hey, I want to publish a message to animal science from a sensor collected at say somewhere in Holland. And then here, I subscribe to the particular topic on this server. I can get the message. Now think about this, how helpful this would be to integrate all the data together. For most of the data, sensor data, this MQTT is a default choice. There are some other different solutions, but this one seems to be working best. And there is a committee trying to make this. I believe it's already ISO standard, and that have been integrated into different softwares, and now that's getting more and more popular. And this is the one we have been using to sending data, from different sensors to our server, and this server can keep a copy of this. And each column, each topic is just one column in your database, right? It's a time sequence data. You have one column and just keep collecting data. And on the user side, it's very easy to use. It's just, again, it's one line. You say, okay, I connect to this server, to this topic, give me a message. It keeps sending you a message in real time. It's just how you use it. Now think about this. If you have someone give you this, you have a sensors on your farm, how will you use it? You need to set up some client side. You need some computer on your client side. That's why I'm talking about edge computing. On that side, all the sensors can send all the data to different connected devices. The device can run a simple client, MQTT client. This is a server I'm running. Broker is like a server sitting there somewhere. But the client side can get the data and send it to this broker. And the broker will just figure out how to send it out to others. It's a very simple model, but it's really, really powerful. Can do many, many things. We have been using this for collecting data collected from sensors to Unreal Engine. We use this to send the data to web-based interface. We use this data to collect real-time data and build up our machine learning models. So we are using this almost everywhere for our project. Now, consider you have data collected. The next thing you worry about, store the data, the data storage. You can have local file systems. Could be just a file if you are using SQLite, which is actually every phone now. Not just my Android phone and iPhone. They have SQLite database inside. It's just a file. This file could be loaded into your memory. That's why it's really fast because everything is running in the memory. You don't need to load the file. So whenever something changes, you need to save it. It will save it to a file. It's just one single file. Not like complicated databases. SQLite, which is a SQL database, very powerful one used by a lot of projects. Smaller ones, big ones. And then you have a distributed file system. You could have a system sitting in Europe, US. That's all those big companies are doing. They have systems synchronized automatically. And if you are a user here in US, they will give you, hey, this is the system you guys can use. This will give you quick access. Cache all the things you downloaded from website. That's why YouTube video is so fast because they have a local servers, computer servers caching all the things you downloaded so you can share to the local people not so far from your place, your area. Then they have other servers, data centers, big data centers. They keep archiving and backup your stuff. That's why they have a lot of redundancy. Whenever something bad happens, you can still bring up your data. There are a lot of algorithms to figure out the best way to save your data, archive data. It's a distributed file system, which is actually sometimes very fast and very safe. Cloud storage, you all use AWS one way or another. You are using Google Cloud one way or another. Either do the computing there or store your images, pictures in. And then database system, just a regular database system, SQL database or no non-SQL database, so different databases types. And then finally, the data warehouses. It's kind of like a Dropbox kind of thing. Upload your data, store there. They don't really care what your format is. It doesn't need to be a database. It could be any file, any format. And Dropbox, any other, I'm sure there are many other things there. So you can use those. This cloud-based, local-based storage solutions, or you can do the hybrid. So talking about cloud computing, now it's almost everyone's using that. Almost everyone, as long as you have an internet access, you are using that one or another. Whenever you create a new account, on some website, they might be using AWS or Google Cloud to store your data and do some things for you. So again, as I mentioned, we have different scenarios. You can have hybrid cloud, public cloud, and on-premise cloud, which is on-premise is your own, but you can link this on-premise cloud to set up a private cloud. Private cloud could be linked with a public cloud. So the link here is help you to synchronize that, just like when you do the automatic backup, like time cancel, or I'm not sure Windows has like backup mechanism. You can let them synchronize automatically, depending on your bandwidth and also your other services you're subscribing. So that's the kind of deployment for cloud systems. Compare the storage, cloud storage, local storage. The cons for cloud is it's a security and privacy. I think that's a cons. Not for cloud computing. Actually, you give the company, whoever managing your data, access to your data, which is kind of scary. But some people, for some of the data sets, you don't care. You just use that for storage. So that's why you don't want to store your sensitive information on this. Sometimes, once in a while, some hacker will hack into the system. It's not always guaranteed that it's 100% secure. And then you have the problem about control. Sometimes, if the server is down, sometimes even Google, they have failures on the servers. You cannot get the data whenever you need it. Sometimes, but it's not always happening. But the good things about cloud computing is that you don't need to pay an initial setup. You don't need to buy a big machine for $1,000, $2,000 to buy a server, or even more. You just need to just pay, $100. Just use some server for 1 month or half several months, or just $10, whatever, to get you a virtual machine up and running. And also, time solution is pretty fast for cloud computing, and you can easily scale. If you can run something on the cloud node quickly, you can easily scale this to multiple nodes if you know how to use them. And also for storage, it's almost unlimited, you know, as long as you have money, you know, they can provide almost unlimited access to the storage they have, up to multiple petabytes or etc. And also reliability on the cloud is definitely much better than machine. A machine might be failing and you won't be able to bring it up. Your data could be completely lost, but on cloud, you really have a backup and it's better. For data processing, whenever you get data, of course, you get some bad data sets. Sometimes you have missing values. Sometimes the formats might not be good. Sometimes you put the wrong metadata. You know, there are many things could go wrong when you're maintaining data. So that always a good practice is to keep the raw data somewhere in case something goes wrong. Always check the raw data, and then there will be a lot of effort getting into this data processing about how to do the data integration. If you have data from different agencies, you know, if you look at it, they have probably the same column but timestamps, but sometimes you see they're not overlapping properly. You need to figure out how to align them, group them, and there are a lot of things that need to be done for data integration. Unfortunately, there have been a lot of work by the US government and the different agencies. They're trying to unify the data formats and make it easier for researchers. And the data transformation is mostly data formats related. Sometimes you want to do some aggregation, like, you know, do some sorting and all those kind of things. If you are dealing with data, that's a pretty regular operation. This could be done, you know, depending on size, could be done easily with Excel or Python. So the goal is to convert information you collected to the information you need. For the example, we want to check the status of the cow. We train our model to take an image as an input. We want to see if this particular cow, in a particular location, is standing or lying down, doing some of these things. So that's an ongoing research. I don't think we have that in the model, but we do have them in our mind. For data analytics, that's something we're doing for feeding bank. We do have a camera set up to use the computer vision technologies to estimate how much food a cow is eating. Currently, all these feeding banks are already measured. We have the measurements. So we are using the measurements from a feeding bank. Those are electronic sensors to measure the weight. And we use those as ground truth to train our model. So our model can, in the future, our model can look at the image inside each feeding bank and estimate the volume and weight for the food. Hopefully, we are still working on that. But at least, if you want to not sell, but say, hey, give this to farmers for them to use, they don't need to buy expensive weighted, scaled feeding banks. They just get a couple cameras setting up. They can estimate under certain criteria, not so accurate, of course. There are always errors there, but you can roughly estimate how much food each feeding bank contains or got eaten by the animals. So that's something we have been working on for a while, and Iglu was leading, or Yalong P from our group says it's just submitted a paper recently for review, and we'll be continuing working on this kind of effort. I think I'm going probably too slow here. I put some more slides here just to give you some understanding about deep learning. Some of you I know have never done anything about deep learning, but this is trying to just to show you how all this magic works. Right? I'll go through this quickly, but we can talk about this after doing a dinner or after dinner. We can meet at some time. I'm more than happy to do that. I have been teaching this deep learning courses at ASAS-NANP for 5-6 years. I have been there for 5-6 years. I'm teaching on this. So for the computer to see the image, it's nothing more than numbers. This cat, we see it's a cat because our brain have been trained to recognize this particular object in this shape as a cat or sitting on top of probably a trunk. But for computer, it's just numbers. This RGB image give you RGB 3 channels. I'm just showing you one channel. If you want to see RGB 3 channels, every channel is the same. All the numbers are going from 0 to 255. That's representing the index of the color for each channel. So we have 3 channels put together, we get an image. Just look at it. How, if you're a machine, how can you tell it's a cat? Just look at the numbers, right? There's no way. But of course, a machine looking at the numbers differently, that we can imagine. So the whole purpose for the computer vision, all the things we're doing with cameras, is trying to, for example, this is just one of the examples here, trying to take this image as an input and output a small vector, like here, I have a vector of 4 numbers. Okay, assuming I want to train my model to tell if it's a cat, it's a dog, or hat, or mug. These 4 objects. If I have 1,000, I will have a vector of 1,000 number element. But here I have only these 4 different kind of objects I want to train model to recognize. So now let's step back. Now we are trying to give this input image with, like, assuming it's 1,000 times 1,000 pixel. That's 1 million. If we just look at just 1 channel, it will be 1 million numbers. That's 1 million numbers. That's 1 million dimensions. That's 1 million columns. But you train it, that's 1 million features. Every pixel is an individual feature. If you just feeding the data to the machine, that's kind of a lot, right? If you look at that. Now, I want to use a machine learning model to extract this key information by converting this 1 million numbers into only 4 numbers, each number representing the probability of this particular image belongs to a certain category. If the first number is 82, the order is fixed. The first number is cat, second one is a dog, third one is hat, last one is a mug. But the value itself representing the probability, almost like confidence. So this model, machine learning model, is trying to do this, mapping this 1 million number to 4 numbers. That's the whole thing we are doing. It's just a function, nothing more than a function. Okay, so this is the most important algorithm used in machine learning, deep neural networks, mostly deep neural networks. So to the left here is a rectangle. This square contains the data. Every row is a data. Consider it's a data. What the data is? It's all the blocks, all the squares that are showing. Those are each pixel of the image. I'm just showing 4 or 5, but you can imagine you have 1 million pixels like that. The very last column, the circles, very last column of this data set box, it is a label. Cat, dog, we have 4 labels. So with that, all the pixels as the input, for example, 1 million pixels, I'm just exaggerating a little bit, but consider you have 1 million numbers as the input. I want to tune my neural network, all the numbers, all the weights on each circles in the middle, to give me the final output, which output will be corresponding to 4 numbers. I mean, in the previous example, that can give me the prediction of what kind of image what kind of object is my image. So it's called the supervised learning mainly because you know what each image is. That's your label. You know it's a dog, it's a cat. Someone needed to label data for you, or you have to do it yourself. Prepare the data. That's why it's time consuming for me to ask my student to label, say this cow is standing, because when the cow is standing and when the cow is lying down, there are different images. So I needed to ask myself to label each one, so I can put a label there and I can train my neural network. Now the tricky thing is like this. So that's the most important part. At the very beginning, you don't know what's your weight for each circles. You have no idea. You start with random numbers. Even if it's a random number, you'll get some number out. By plugging all your input, put into your neural network, you put all the weights, all your neural network, all the circles in the neurons. All the neurons contain just random numbers of the weighted average of your input and weighted average of the first layer, second layer, etc. Finally, you get output. That's a random number, finally, because you are all carrying random numbers. But you get some error calculated based on your targeted output. Assuming this error is 5. Let's just so assuming we can put a number there. We know this error is 5. The next thing is that's how the training is working. Let's increase the weight of the one of the neurons. Just one. We can have millions, billions. Sometimes for the big neural networks, they have billions of neurons there. Let's consider we have only one neuron. Let's change the weight for that particular one. Make it bigger. I change the line a little thicker. You can represent. You can see this previous one and this one. Right? It's getting thicker. Basically, I want to give more weight on the particular neuron at the top. And by doing that, as you can imagine, the error will be different because I changed something inside my neural network. And the error is bigger. So what should I do? My goal is to minimize error. I want my model to give me the prediction. I want to minimize it. So what I'll do, I'll go back to make my weight for the particular neuron to be smaller. That's gradient descent. Some of you probably already learned that, right? It's gradient and descent. By making that smaller, my total error will be getting smaller. I can keep doing this for every neuron. I could have 1 billion neurons. I can keep changing each one of them. That's why, training a neural network is so expensive. You need to buy very decent NVIDIA GPUs to do that because it's more efficient than a GPU to train this kind of neural networks. So as I mentioned, the model, no matter it's a neural network model or machine learning model, it's nothing more than a function. You give some input, you want this model to give you some output. Could it make predictions? Could it just calculate some derived quantities? The neural network, it's kind of has a very, has a very special property. It can not only predict your value, but also predict your derivatives. And you can consider neural network as a universal approximator for all kind of like functions. And all you are doing now with the training process is trying to figure out this function. But this function could be constructed with a predefined neural network. And all you do is just tuning all the parameters inside this predefined function. And this parameter tuning is called training for neural network. So this is probably one of the mathematical equations. Consider for each neuron here, you get a function that's a nonlinear function. It's just weighted average of all the number from previous layer. You do this layer after layer for each neuron until you get to the final output. So you can compare the expected output, which is your ground truth, you already have the labeled data, and your predicted output, which is based on your network. Could it be wrong? Could it be completely wrong? Could it be random? But you can always get error. You can always go back and change your parameters, keep tuning with training your model many times. Your error getting smaller. You can say, okay, I can make my model can give me 80% accuracy. When I test it, then you can probably just start using your model for real world scenario. So this is more rigorous definition about loss function. That's the one you want to minimize. It's like least square method. You go back to the derivative, get a gradient descent method. You know how you change your weights, and then you get your model trained essentially. Okay, so last we'll talk about some practical case study. That's camera data from our beef center. One of the I believe these are the new ones we installed. There were some older ones. So what we want to do here, we want to put everything together. I taught a lot of things. It's actually, as you see, it's interdisciplinary research, right? It's computer science, animal science, machine learning, statistics, and many other things you can think of. So we started with the physical livestock, and just cameras, anything. Not cameras. Sorry. Here's talking about a real thing. The image I'm showing is just showing the real thing. I'm not trying to say here this is a data item. I'm just livestock here is representing the real object, real farm. Now you have some precision farming tools, cameras, other sensors. Those are the tools you want to purchase, you want to develop, you want to install yourself just to get some information recorded. Then you need to get the data collected. The data collection could be historical data. You can keep collecting data and store them, or you can do the data streaming using MQTT and other brokers. Then you put it into your model. There are statistical models. You based on data, historical data you have, you can come up with some model. This model could be improved if you get more data, as you may probably easily expect. There are also machine learning models. You can also, whenever you get new data, you get the data labeled. You get more information about the data. You can train your model. The model can give better prediction. And then finally, based on the output, you can make predictions. You can make decisions. About what I should do about it, etc. So I got this QR code, but I'll share the slides with you all afterwards. This QR code link is linked to the spreadsheet that Igloo Maddie's created, and we have the shopping list. We have all the links and also the price there. So it's for our research project, it's kind of expensive. We got like totally how much? $2,000, something like that. But you can easily, if you don't want to install so many, you can easily get it down to a couple $100 probably. You don't need to install all the things we have. Some of those, install the camera. It's just a very simple camera. You can buy online as long as you get your very small, retired laptop. You can just hook it up and put it somewhere, and you can start doing something like this. So for the livestock tracking, this is what we are doing. I don't think I'll have time to run this, but I'll be more than happy to talk with you after this, and we can have a quick question and answer session, and I can show you all later on. So what it does, basically, we have a camera running, but we currently just, for demo, I just create I take a video strip, a video clip, and the machine learning model will take a video clip as an input. It will output the XY position on your screen, and I use XY position. I ask my students to draw the icon, just showing the movement of the cows currently. It's if you have any bus tracking system, it's the same thing, but they have their GPS system installed in the bus and send images to as a base station or to satellite, or mostly to local station. They get the information from a satellite for the GPS location. They send it to some base station. They share the data back to the central servers, and they can get the tracking. But this one, we're just using the camera, nothing more, nothing less. We're not using any GPS. It's just camera. We didn't install anything on the cow, and we can keep how they're moving. Of course, this is a demonstration, but it basically shows you how things are working. I think I have. Let me just show. I'm not sure if it's one is working. Can you all see my scroll? Let me increase the. So that's the backend. That's how you get everything set up. So I activate my Python environment. I have all the packages installed already. So the first thing I'll do, I'll run my backend to analyze. Probably I want to do the backend. I have some. I believe there's a how for want to do anything else. So what this one does, actually, if you can see the. So I believe it's waiting for me to click the, let me see. So what it does is it takes a video stream and the input. It's trying to identify the bounding boxes, and you can see sometimes you'll miss one. It's mainly because sometimes the view condition is different. This bounding box could be giving you the location of the cows. It's a very, very standard way to use, machine learning to do this. It's called the pattern we're using for the ULO, and it started with a very simple, algorithm as an entry level object detection packet. Now it's already version 8. And it's people have been adding more and more information and getting the algorithm improved, and also more data used to train the model. And this one, we didn't even train our data set. We just use it to detect the cows inside. And when we try to do the gestures detection, whether standing or lying down, we need to get our own data set labeled and trained. Okay, let me. This one seems not. Well, I'll show you all the website. So what it does, so that's the one I showed you all, is to do the bounding box detection. Another one I'll show you all a bit later on, after this, is to get the information detected, get the image processed, every frame of the video stream processed, and getting the XY position of the center of the bounding box, and send the data to MQTT broker, which is running on the cloud service. It's not belongs to NM, it's a public service. Everyone can subscribe to it, just for demonstration purpose. And then I have another server running on my local machine. That local machine will subscribe to that particular topic. And then I can get this information visualized on a web-based interface. So think about, even though it's simple demonstration, but you can think a lot of things could be done through this kind of collaboration. You don't need to know who is doing that. As long as you know the topic, the particular guy tell me, hey, this is my data, check it out. You can directly run it, you can visualize it, and you can do, many other data sets could be shared in a similar way. Methane emission of the farm, and as long as you have the infrastructure set up.